So 7.1b will be about verifying trig identities. Yesterday in 7.1a, we simplified. Today we're actually going to verify it. And our lesson goal is to do what we did yesterday, produce these equivalent statements, these simplifications. But what we're going to do is connect one trig expression to another to verify. Now, I sort of been playing footloose and fancy with the term identity. I've been branding it out without really defining it. In mathematics, the term identity is actually very specific. An identity is something that is always true. I guess I should write this down. The word identity is a statement that is always true. For example, the Pythagoras identity. Notice how this statement uses a variable, theta. Well, it doesn't matter what angle you think of. Think of any valid angle in the whole universe. If you take the cosine of it squared and add the sine of it squared, I promise you it will always equal 1. Right? So this is an identity. This statement is true for every single angle you think of. But not every expression or equation is an identity. For example, if I had like sine theta plus cosine theta equals 1. Right? This is true for all angles. But this statement is only true for certain angles. Take a random angle, say pi fourths, plug into here, and you are not going to get 1. Right? So it's very easy to check if something is not an identity. You just produce a counterexample. It's very easy to show a statement is false by providing a counterexample. But how do you prove that something is true for everything? How do you write a trig proof? Well, this is where algebra comes into play. In order to prove an identity is truly an identity, we need to be able to produce a series of algebraically correct steps that connects one side of the equation to the other. Now, just like with 7.1a, this is one of those lessons where you just got to practice at it. It's one of those, you either know it or you don't know it. There isn't a formula to follow. There isn't a blueprint that you always take. It's just something you have to play around with, and the only way you can get better at it is if you just practice. But like with yesterday, I do have some hints, tips, or guidelines for you. Right. So tips or hints for verifying identities. For me, start at the side that looks more complicated. That usually means it has the most pieces, the weirdest symbols. It's sort of like doing trig proofs is sort of like assembling something, right? You'd rather have more tools, more pieces to play with, more Lego blocks to construct something than not. Now, of course, this is very subjective. What I think is complicated might be different than what you think is complicated. But over time, you're just going to get a feel for, what side to start with. And the good rule of thumb is, oops, didn't mean to shrink that. And a good rule of thumb is whatever side looks, for lack of a better term, complicated, is usually the side to go with. Even though these are algebra proofs, you should always remember established trig identities. So this is just like yesterday's lesson. You can't forget the reciprocal identities, the even-odd identities, the Pythagoras identities, and all the hints that I gave yesterday are still valid. If I see a trig function being squared, think of Pythagorean identities, especially if I see a 1 attached to it. If I'm completely stuck, you convert everything to sines and cosines. Remember your good algebra rules. If you If you see common factors, factor it out. If you see fractions added or subtracted each other, find the LCDs. So those are sort of my hints, in addition to yesterday's hints, in order to verify trig identities. Start on the side that looks more complicated. Remember your established trig identities, and I guess I should write it down. Remember yesterday's hints. If you see a trig squared or trig squared plus or minus 1, think Pythagorean. Convert to sines and cosines if stuck. But other than that, there really is no teaching with this lesson. I hate to say it, you just have to know it. But, we all have to start somewhere. And when I first learned or started out doing trig proofs, I had to have someone do it for me. I had to see the logic, the thought processes, and then you just naturally incorporate into your own thinking. So I'm just going to pick random examples from the practice, nothing special about these examples, but let's just do a handful just so you can see it in action. So suppose I ask you to prove that if you take a cosine and you multiply it to secant minus cosine, that it equals sine squared. Now, the answer to these proof problems isn't the last line. The answer is actually the work. So you sort of need to write stuff down. Doing it, quote, in your head is not a valid response because I need to see the logic, the thought process. Also, please be organized. Think of this as writing a final draft to an essay. I don't want, step 1 here, and then you do step 2 over here, and then step 3 over here, and then step 4 over here. Don't make it all complicated. Make it nice, smooth, flow, everything connected. So the first thing I want to do is start on one side. Now, my hint is it doesn't really matter what side you start with, but I like to start on the more complicated side. And the left-hand side seems to have more pieces to play with. So I'm going to start on the left-hand side, and that's how I'm going to declare it. Left-hand side equals. And then just, do stuff with him, right? Some people like to rewrite the problem. Others don't. I am a firm believer of showing all my work, so I'll go ahead and rewrite it. And then what you want to do is keep this equal sign lined up, right? And then work downwards. Now, everything you do from this point on should be a true, valid math step. Notice I'm only focusing on one side. You do not want to balance the equation like, I'm going to divide both sides by cosine. You cannot do that. You need to start on one side and reach the other. It's sort of like laying down breadcrumbs. So let's just do a math thing, right? What do we typically do in algebra when we see stuff outside a set of parentheses? You distribute. So we'll go ahead and distribute. So that's cosine theta secant theta minus cosine squared theta. And I should know that secant is 1 over cosine. And then, of course, cosine times 1 over cosine is 1. And we should know from Pythagoras' identities that if cosine squared theta plus sine squared theta equals 1, then 1 minus cosine squared theta, if you subtract both sides by cosine squared, gives you sine squared. So this equals sine squared theta, which is the right-hand side. That's exactly what we wanted to show. So what is my final answer? My final answer isn't this last line. My answer is this whole guy here. Your work is the proof. Remember, a proof is a chain of logical arguments. You're making an argument that this guy here equals this guy here, which I believe we have accomplished. Now, typically at this point, mathematicians would write QED or some other symbol to indicate to the reader that the proof is done. I like the tombstone symbol, which is just a black square. That's it. You wrote your very first trig proof. So I hope you guys see that it's the same logic as yesterday. Just apply algebra knowledge to trig expressions. The only difference is in a proof problem, you can't balance the equation. You have to start on one side and work your way through logically to the other side. Some problems will require a little bit of thinking, and that's sort of half the fun, right? It's not fun to do things that are automatic. So you are going to run into situations where you're not going to get it the first time. You are going to get into situations where you go down one path and it's completely wrong. And that's okay. Just keep plugging away. Try one avenue. If you're stuck, you don't know what to do, try something. If it's wrong, the worst case thing is you just wasted some time and some paper. That's why I like to do this on a whiteboard, because I can easily erase. Let's just do another random example here. Suppose I ask you to prove that 2 tangent of theta secant of theta equals 1 over 1 minus sine of theta plus 1, minus 1 plus sine theta. So let's go ahead and prove this. I need to start on one side. I think everyone would agree that the right-hand side looks a bit more complicated. Everyone loves fractions, right? So here's my answer. Right-hand side equals, and you know me, I like to rewrite things. Since I have fractions, I'm going to leave some space, because typically with fractions, you always want to do the LCD, which in this case, that's what we need to do. That's what we talked about. I don't care the fact that we're doing trig. This is regular algebraic expressions. So here I'm subtracting 2 fractions. In order to add and subtract fractions, you need a common denominator. So the common denominator is just each other. So the left fraction needs a 1 plus sine theta. The right needs a 1 minus sine theta. And as I said yesterday, I typically don't multiply out the LCD unless I need to. So let's just leave it in factored form for now. Sometimes it works, sometimes it doesn't. So distributing the numerators, we have 1 plus sine theta. Be careful with subtractions. Anytime you subtract a fraction, you have to distribute that negative. So think of this as distributing a negative 1. So if you distribute a negative 1, it becomes a minus 1 plus sine theta over 1 minus sine theta, 1 plus sine theta. Here, we can see that the 1's cancel out, positive 1, negative 1. But we have 2 of these signs on top. Nothing will cancel out with the denominator, so that signals to me that I should probably multiply out the denominator. So this is a case where nothing cancels, so you go ahead and do multiply it out. So we have 2 sine theta over 1 minus sine squared theta, right? Difference of 2 perfect squares. What else? Oh, I see a trig function being squared with a 1 here. So as my earlier hint, see a trig function being squared, you think with a 1, you think of Pythagoras' identity. So I know that 1 minus sine squared is cosine squared. Now, in all of this, we should always remember our goal. So I always like to write down my goal. What is it that I want to end up with? Well, since I start on the right-hand side, I want to end with the left-hand side. So I want to end with 2 tangent secant. So I look at what I have and try to figure out, do I have the pieces that I want? Well, I know my final result should have a 2 in it, so that's pretty good. I'm going to keep that 2 there. I'm not going to mess with him. Somehow I need a tangent secant from the rest of it. Well, I know that tangent is sine over cosine, and I do have some cosines, except I don't have a regular cosine, I have a cosine squared. So just use the definition of squared. I know that squared means something multiplied by itself, right? Well, there we go. We're basically done. Sine over cosine, we know is tangent, and we should know that a cosine in the denominator, which is the reciprocal, is a secant. So this equals 2. This gives us the tangent, and this gives us the secant, which is the left-hand side, the left-hand side. We are done with the proof. what a journey. We have mathematically proved that if we start with the right-hand side, that is equivalent to the left-hand side. In other words, we have verified the original identity. Now, you can typically prove trig identities with what they give you, but sometimes you may have to add extra things or use an algebra trick. So this one here will involve a quick algebra trick. So suppose I ask you to prove cosine of u, or let's use theta, over 1 minus sine theta equaling secant of theta plus tangent of theta. Typically, most people would start on the left-hand side because they think fractions are more complicated, so we'll start with the left-hand side. Now, this is where we're sort of stuck. I don't see any squares, so I can't use Pythagoras identities. They're already in tangents, or excuse me, they're already in sines and cosines, so there's nothing to convert. And I only have one fraction. I'm not adding or subtracting fractions, so I can't use the LCD. What can I do? Well, I could just start over and start with the right-hand side, or this is sort of like a Mr. Vo hint here, right? So this is really on math hint, this is Mr. Vo hint. Normally, if I'm stuck, if I see a binomial, I think of conjugates. For some reason, in math, not in just trig, but in all branches of mathematics, conjugates seem to be like the answer to everything if you're stuck with what to do. So in this case, I am stuck, but I do notice I have a binomial here, 1 minus sine. So I'm going to multiply top and bottom by his conjugate. So I'm going to multiply by 1 plus sine, 1 plus sine. Right. Now, you remember my previous hint when I said typically if I find the LCD, I leave the denominator in factored form? Well, my other hint is anytime I use conjugates, I typically do not multiply the non-conjugates. This is what I mean. I got the conjugate from the denominator, so I will multiply these guys out. This guy did not have anything to do with the conjugate, so I typically do not multiply him out. I typically leave it in factored form. But again, there's no harm if you do multiply it all out. You're just going to have to refactor him out. So in this case, I'm going to leave the numerator in factored form because he had nothing to do with the conjugate. But I will go ahead and distribute the denominator out. That's the product of two conjugates, which is the difference of the perfect squares. Now I do have a trig function being squared with 1, so I can use Pythagoras' identity. And I should know that 1 minus sine squared is cosine squared. And this is why I leave things in factor form. I have a cosine on top, cosine squared on the bottom. I can cancel out one of the cosines, and this is 1 plus sine theta over cosine. That's great and all, but it looks like I'm still stuck. That's not what I wanted. So remember, you always want to keep in mind your goal. So our goal is secant plus tangent, right? That's our goal, secant tangent. You can use your goal to help you figure out what to do. Notice how we ended up with one giant fraction. But I know for a fact that I should end up with two separate pieces. This is a classic instruction or classic indicator that, you know what? I shouldn't have one giant fraction. I have two separate pieces. I should have two separate pieces, so let's separate them. Let's split apart the fraction. So that gives us 1 over cosine theta plus sine theta over cosine theta. And lo and behold, that gives us exactly what we want. 1 over cosine is secant. Sine over cosine is tangent, which is the right-hand side. We are done. So, I mean, these guys are pretty cool. It takes practice. I hate to say this, but again, there's no formula to follow. There's no blueprints. Every single problem is different. You just have to build up skills. You just have to build up techniques. You have to build up thought processes. And the only way you can build that up is, through practice. The last example I picked is just to show you a different method. typically, stereotypically, all of these problems should flow from one side to the other. So notice all the previous examples, I started with one side, made one giant chain, and ended up with the other side. If it helps you, right? Let's call this comment. You can work both sides independently and meet in the middle. I really don't like doing this because, I don't know, just maybe it's my elitism, my snobbishness. I think these trig proofs should be able to go from start to finish every single time. But, I've been doing this for a while. I have more intuition. So, of course, I can see things that you guys may not immediately. So if it helps you, you can actually work both sides separately, and if you just notice that you all meet in the middle, well, technically you've proved it. I only ask that you do this as scratch work and make your final answer one long continuous chain. So for example, suppose I ask you to prove that 1 plus cosine theta over cosine theta is the same thing as tangent squared theta over secant theta minus 1. You might be going, oh no, both sides look complicated. They're both fractions. They both have a binomial. I don't know what to do. I don't think I can go from one side to the other. So if you want, let's just pretend I start on the left-hand side. All right, I'm going to start on the left-hand side. 1 plus cosine theta over cosine theta. I don't know. I see this cosine over cosine. I want to cancel them out, but I can't because of this plus here. So maybe let's just let me identify this as scratch work. Let me split apart the fraction so I can do the cancelization. So this gives me secant theta plus 1. Oh, that's getting me close, right? I want secant minus 1 in the denominator, but this is good enough. What can I do with the right hand side? So if I have tangent squared theta over secant theta minus 1, well, I do have a trig function being squared, so I'm going to think of Pythagorean identity. And I know that tangent squared theta is secant squared theta minus 1. Now, there's something funny about this. They're very, very close, except this is a square. Well, I should know that this is the difference of two perfect squares. Remember a squared plus b, a squared minus b squared, right? A squared minus b squared is square root minus square root plus square root. So we can use that to our advantage. So I know that this is secant theta minus 1, secant theta plus 1. Hey, these guys canceled out. And what am I left with? Secant theta plus 1. So you see here how we ended up in the same spot. Now, some people will say this is fine. You proved it. You proved that the left-hand side equals the right-hand side because you independently showed that the left-hand side and the right-hand side equal the same thing. And that is 100% true. I'm only going to ask you to take the extra step further, write it up in a nice, neat, clean final draft. So as my final draft, all you would have to do is just connect the dots. It doesn't matter where you start with, left-hand side, excuse me, or the right-hand side, right? So I'm going to start with the left-hand side just because I feel like it. And literally all you got to do is just copy down what you wrote. So it's 1 plus cosine theta over cosine theta equals, we split apart the fraction. We simplified this to secant theta plus 1. So we've gone this direction. Now all you got to do is just connect the dots and go in that direction. So from secant theta plus 1, it looks like we did the conjugate, right? Top and bottom. So I know this is true. secant theta plus 1 is the same thing as secant theta plus 1 times secant theta minus 1 over secant theta minus 1. All we did was multiply top and bottom by the conjugate. The numerator is secant squared theta minus 1. And then we know that secant squared theta minus 1 is equal to tangent squared by the Pythagoras identity, which is the right-hand side, right? So we proved it. We have mathematically shown that the left-hand side equals the right-hand side. So that's what 7.1b is all about. It's just taking the same things that we talked about yesterday. Use regular good algebra in the context of trig. The only thing that's different is instead of just merely simplifying, you are proving a statement, and that is simply chaining, like putting breadcrumbs together, connecting one side to the other. So go ahead and have at it. And again, the only way you can get better at this is if we practice. So please, please, please practice.